Hello, thank you for tuning in today. My name is Sam Ogden. I'm a Ph.D. student with the CakeLab at Worcester Polytechnic Institute, and today I'll be presenting work I did with my advisor, Dr. Tian Guo, called MDInference. The big idea behind MDInference is that mobile inference frameworks must be mobile aware. That is, any framework for mobile devices must take into consideration the goals and constraints of mobile devices and applications. So first off, what's mobile deep inference? In short, mobile deep inference is using deep learning models on mobile devices. You've almost definitely encountered this, but let's give some straightforward and solid examples. The classic example is image classification, because it's both easy to understand and to play with on mobile devices, as well as having a wide range of pre-trained models performing this same task. In image classification, an input image is given, and the deep learning model is used to infer what is shown in the image. In this case, it classifies this image as a dog. Another common use is speech recognition, this is used in virtual personal assistants for understanding users and responding to their needs. These take in speech and use a deep learning model to perform natural language processing and search for relevant information. While these are both very common, in this work we focus on image classification since it is a more straightforward example and consists of a single deep learning step. Deep learning on mobile devices has two core goals. The first is to improve accuracy, and the second is to decrease latency. Accuracy is important because the ability to determine that this picture shows a European Doberman. Latency is important because this information should be available to the user as soon as possible. Throughout this presentation, we typically use a 250 millisecond as a target for this latency. These two goals, accuracy and latency, are often challenged by the constraints on mobile deep inference. These constraints are not unique to mobile devices, but the extremity and number of them is. The first constraint is the dynamic network environment that mobile devices exist in. This network connection can quickly change, and exclusively relying on it is risky at best, in some cases can make inference impossible. The second constraint is on-device resources. Mobile devices have to be just that, mobile, and they need to have a battery that lasts all day. This means that they have less powerful hardware that's geared towards conserving energy. So while we have image classification models that can outperform humans, running them on mobile hardware will have unacceptably high latency. This in turn ties into the final constraint, which is end-user awareness. Mobile devices are held by humans who want accurate results, and they want them within a reasonable and predictable amount of time. While these are our overall goals, we need to remember that balancing them is important, since end users are holding the device. This all leads to the core question of mobile deep inference, which is how to balance accuracy and latency while being mindful of these mobile-specific constraints. To do this, we propose MDInference, which is holistically designed to be mobile aware. We designed this hypothetical framework specifically to balance these mobile goals and constraints. MDInference targets and achieves two main goals. First, we want to provide high accuracy inference by using higher accuracy models whenever possible. Second, we want to remove the risk of latency-based SLA violations by ensuring that every time an inference is requested, we have a result for the user. We do this by building on the existing approaches for mobile inference and leveraging and combining their advances to ensure that mobile inferences are mobile aware. These frameworks approach mobile inference in one of three ways: on-device inference, shown here on the left, in-cloud inference, in the middle, and hybrid inference. On-device frameworks allow for executing models directly on-device. This leads to high-accuracy models not being available for all devices. Here, we see the execution latency and top 1% accuracy for 22 pre-trained image classification models on 3 different devices. In these two cases, the same model on different devices can be seen to take different amounts of time. The lower comparison shows the difference of being above and below our target threshold of 250 milliseconds. The upper comparison shows that the same model on different devices can have an execution latency difference of over 5 seconds. This leads to having to use low accuracy models on device. The horizontal line marks the accuracy of the most accurate model we can use on our Nexus 5 within our 250 millisecond time constraint, which is about 10% less accurate than the best available for our model for our Pixel 2, and 20% lower than our most accurate available model. Finally, while having a wide range of available models is helpful, it requires the developer to choose the appropriate model either on a device-by-device basis or for all devices at once. The models highlighted, for instance, would be the fastest models for the Nexus 5 or the most accurate model for the Pixel 2. These choices may be appropriate for particular applications, but choosing between them means making a static trade-off. In many cases, they use in-cloud frameworks. In-cloud frameworks instead approach this problem by using powerful servers to run high-complexity models with low execution latency, often by taking advantage of accelerators such as GPUs or specialized ASIC hardware. This has the advantage of letting all devices leverage high-accuracy models, but runs the risk of undue network latency. This is fine under ideal conditions, which we see in campus Wi-Fi and LTE, which typically have low transfer time. This figure shows the network transfer for input images on 5 different mobile network types. These images were pre-processed and were approximately 330 kilobytes in size each. Campus Wi-Fi and LTE both had low transfer time, in many cases leaving enough time for execution of high-accuracy models. However, the average latency can still be quite high, approaching a 250 millisecond target. Finally, there are outliers on all of these networks, where a single network transfer will take unexpectedly long, leading to a long end-to-end response time. In these cases, network latency makes it impossible to both use a remote model and bound the execution of it. Hybrid frameworks attempt to find a balance between on-device and in-cloud approaches to decrease latency and potentially increase accuracy. They typically execute part of a model in one location, on-device, and then complete execution on the other, if it's determined to be necessary. However, this ties them to a single model since the execution needs to continue on both devices, or both locations, and relies on the network being available in order to transfer the intermediate data between them. This means that a main problem with hybrid frameworks is balancing this trade-off between running on device and running remotely, and leaves them open to all the same issues that exist in both on-device and in-cloud inferences. This is because balancing mobile goals is tricky, and non-mobile aware approaches fail to appropriately consider factors such as network connectivity. We approach this in a different way. We focus on a mobile-oriented design and pay attention to these constraints and goals. Remember, our goals are to improve accuracy and latency, while our main constraints are mobile networks, constrained device resources, and the need to be end-user aware. Therefore, the question becomes, how do we increase accuracy of inferences while bounding their latency? We propose doing this via a two-pronged approach. First, we select from a range of models based on their execution latency in order to improve accuracy. Second, we use on-device models to bound latency and prevent the impact of long network transfer delay. Our hypothetical framework to test these ideas is MDInference. We use it to deliver inferences for an image classification task. It is a hybrid approach which submits requests to the cloud and duplicates execution on device. MDInference consists of two main components. The dynamic model selection component leverages functionally equivalent models to dynamically improve accuracy based on the impact of the network. A functionally equivalent set of models is a set of models that all perform the same task, such as image classification, but with the different trade-offs between accuracy and latency made for each of these models. This means that some may be particularly fast but have low accuracy, and others may be slow but have high accuracy. This allows us to adapt execution time to the network behavior. The request duplication component duplicates requests on device using a low latency model to ensure that no matter what the state of the network, inference results will be available for the end user within a bounded latency. Our dynamic model selection is based around the key insight that we can adapt execution latency to the experienced network latency. We do this via a three-stage algorithm. First, we estimate the time budget as the target latency minus the network latency, and select a model that is the highest accuracy model that is predicted to complete within the time budget. Second, we expand to a set of similar models, which we call the exploration set, which include models that have an acceptable average latency, but an unacceptable predicted latency. They may have a standard deviation too high to be predicted to finish within time. Third, out of this exploration set, we pick a final model based on a combination of accuracy and latency via a probabilistic calculation utility function. We use this exploration set to ensure that we consider models that may be experiencing transient issues while still tending towards safe and accurate models. This exploration is particularly important because many models do experience short-term transient issues such as queuing delay or inaccuracy due to moving objects within the frame. We see how this works by comparing the approach of MDInference to a number of other algorithms. We compare it to pure random, which selects a random model, related random, which picks a random model from the exploration set, and related accurate, which simply picks the most accurate model from the exploration set. Each of these algorithms was simulated on a network with an average round-trip time of 100 milliseconds and a standard deviation of 50 milliseconds, with access to the 22 models used before. The execution latencies for these models was measured on an AWS P2X large instance with a GPU accelerator. We see two things. First, we see that MDInference and any time budget aware algorithm can stick to the target SLA, ensuring that we do our best job to combat the network constraints. This means that even with the network variation, we can return, in many cases, the results within a reasonable amount of time. Second, we see that by selecting models based on accuracy, we can improve accuracy. And even with our exploration set, we don't see a significant decrease in accuracy. This is particularly apparent with the difference between MDInference and related accurate and related random. Related random can be seen to have a decrease in accuracy due to picking a model that has low accuracy. To do this, we used a pathologically bad model that intentionally had only about half of its normal accuracy. Related accurate, on the other hand, by picking only the most accurate model, shows the high end of what we would expect from accuracy. MDInference, even with its exploration of trying out other models, sticks very close to this, demonstrating that our exploration, while providing the benefit of testing whether models are effective or not, is not decreasing the effective accuracy that we're seeing. So how well does MDInference work is the next question. To see this, we compare it to a greedy algorithm that selects models purely based on the SLA and does not consider the network transfer time at all. We can see that this greedy algorithm has significant difficulty in meeting SLA targets, while MDInference does so even at low latencies. Additionally, MDInference constrains the variation experienced. We can see that the one standard deviation bar marked for MDInference is still within the target SLA, while the bar for the greedy algorithm just expands beyond it, showing that it has no attention paid to the SLA target at all, or getting results to the end user within a reasonable amount of time. Finally, at our general goal of 250 milliseconds, MDInference has accuracy similar to that of the greedy approach, showing that as it approaches this point, it meets up and begins providing high accuracy inferences while, along the meantime, adapting to network conditions. MDInference accomplishes this by selecting a model based on how much time it has to execute that particular model. This figure shows what model or family of models were selected for execution by MDInference in that test we just saw. We see that at lower latency, it primarily uses the MobileNet V1 family. These models are efficiency-oriented models, which are designed to have a lower latency at the cost of low accuracy. As we increase the target response latency, we see that the range of models being selected, moving through mobile-oriented models and then slightly older models before primarily using NASNet Large, our most accurate model. This shows how MDInference adapts to its time budget. As the target latency increases, so does the time budget, allowing an increase in how often more accurate but higher execution latency models are used. Another key point demonstrated is that the models used at any given point are not static. Unlike the greedy approach, which always utilizes the same model for all requests at a given target, MDInference leverages a range of models. This is because it is adapting on a per-request basis, allowing it to take advantage of the network variations to select a more accurate model when it can. This accounts for the quick and steady increase in accuracy that MDInference achieves. So far, we've seen that MDInference can bound latency quite well while improving accuracy significantly. However, this can only work so far. As we previously saw, mobile networks invariably have outliers where the delay can take unexpectedly long, which means that no response from a mobile server will meet our 250 millisecond deadline. This means that we cannot just use dynamic model selection if we want a bounded latency response. Instead, we need to do more to ensure that we meet latency targets. Request duplication allows us to do just this. By executing an on-device model, we can bound latency by ensuring that we will have results for the end user. We can use an efficient model which has low accuracy but minimal resource requirements, allowing us to bound latency with little overhead. When doing this, there's two potential outcomes. First, we get results from the cloud-based model using a higher accuracy model than our on-device model. In this case, we use these high accuracy results. Second, we rely on the on-device results due to the latency target arriving before the results return from the cloud. In this case, we use the on-device results and accept that they will be a lower latency or lower accuracy than the cloud results would have been. The question is, when do we do this? To test this, to demonstrate this, we transferred 5,000 images across our university Wi-Fi and recorded the round-trip transfer times. Here, we see 20 randomly selected measurements. Network transfer time is shown in dark gray, with network transfers that were too long to support remote inference highlighted in red. This would be the cases where the execution would have led to a violation of our 250 millisecond execution time or response latency target. For those that could use remote inference, the execution time that was of the model used is shown in light gray. We use three alternative methods for selecting for execution: static latency and static accuracy, which are always picking the fastest and most accurate available models respectively, and then random, which just picks a random model. We see that regardless of the approach, there are invariably times when the network added too much latency. Static accuracy is the worst affected, as it has the longest execution time, and therefore violates the target response time, SLA, the most often. Meanwhile, we see that MDInference rivals static latency as the ability to execute within the target. Since static latency is always using the fastest available model, this means that MDInference is picking this fastest available model in the cases when it's most necessary to produce fast results. Also of note is the ability of MDInference to adapt its execution time to the target latency while picking increasingly accurate models. By staying so close to the target response time, it can in fact provide higher accuracy results. We see this especially when we start to look at the impact of request duplication. We can see that at the same latency target, 250 milliseconds, MDInference provides a much higher accuracy than the static latency. At this point, the static latency approach or static accuracy approach cannot actually is just beginning to be able to return responses within the target response time. Throughout this entire time, before this, MDInference has already been returning higher accuracy results. At this point, it's 35% higher accuracy. And this is due to not relying on the on-device model for results, and instead using the higher accuracy cloud-based models that while static accuracy was relying on the on-device model in order to bound latency. We see the on-device reliance decreases very quickly as the ratio of requests using the on-device model quickly decreases. The accuracy increases as the on-device model usage decreases. While some requests will always rely on this model, as we previously saw, MDInference can improve accuracy over it very quickly as the target latency increases. And at our target of 250 milliseconds, it has an extremely low reliance of approximately 5% on our on the on-device usage. More specifically, For university Wi-Fi, we can see that the on-device usage was only 0.26% once we were at the 250 millisecond target. On residential networks, this improved up to 3.16%, showing how when we experience a range of network latencies and a range of networks that we're using, it's very important to be able to adapt to these and to have the on-device backup, the duplication on device, in order to ensure that we can get results in these cases. This on-device duplication, when coupled with dynamic model selection, allows MDInference to provide higher accuracy while bounding response latency to 250 milliseconds. In this case, we can see that we improved over the static accuracy approach at our target by 1.3% on university Wi-Fi and 7.3% accuracy on residential Wi-Fi. Compared to the static latency approach, which is the one-size-fits-all, we see that we improve accuracy by over 40%. This shows the advantage of dynamically selecting models based on the network time. We therefore see that there are a number of benefits to our holistic approach. Being aware of the specific goals and constraints for mobile devices allows us to improve their performance. By designing MDInference with this specifically in mind, we improved accuracy over static approaches by over 7% and up to 40% while bounding latency and having no SLA violations at 250 milliseconds. We can therefore see that designing mobile frameworks in a mobile-aware manner is critical and can dynamically improve the mobile experience. Thank you for listening. I hope you've learned something, and take some time to read the paper and check out my GitHub repo with all the available code. Thank you.